Great. Thanks everyone for coming along to another SNAPP seminar. This week we have Anton Braverman, who's in the operations group at Kellogg, Northwestern University. He completed his PhD in operations research with Jim Dye at Cornell University, and previously did a bachelor's in maths and statistics at Toronto University. Anton's interested in stochastic modeling and applied probability with applications in ride sharing and healthcare. Though I personally know Anton's work a lot for doing a number of excellent works with Jim, and now continuing that on applications of Stein's method to queuing systems. We can get more accurate formulas for predictions of those systems using Stein's method. And I think we've also done a lot of good work on new ways of thinking about Stein's method, which were inspired by that application area as well. So great to have you, Anton, and thanks for giving a talk.
Thanks, Neil, for the intro. Well, hi, everybody. So coming back to the title is long and perhaps irrelevant. The important thing are the next slides. I want to talk to you today about something which has been has started in my mind at least 3.5 years ago at the last Stochastic Networks conference in Edinburgh, maybe a little bit before then. And today I'm at a point where this project is finally nearing its completion. So the main idea generated 2 papers. One is already accepted, another one is in the review process. And I want to share with you what I've kind of thought about and how this will hopefully be relevant to your setting. So today I'm going to talk about how we use Stein's method for the join the shortest queue system. Why join the shortest queue? Because many people have had interest in load balancing and parallel server systems recently. So I thought that would be a nice application. The talk is going to be structured roughly into 3 segments. The first 20 minutes or so, I'm going to talk about the basics, and this is like a crash course in Stein's method. Many of you have probably heard some of this before, so it may be a repeat. Then we're going to talk about the infinite server system and then the JSQ system. All right, so the central player or the central object of importance in all of this is something called the relative value function. And to introduce it, I want to use the infinite server queue as an example, as a driving example, so that we stay concrete, right? What is the infinite server queue? It's a birth-death process, this Markov chain, Poisson process arrivals with rate lambda, so you get 1 customer, and then exponentially distributed service times with rate 1, right? So if you have q customers in the system, your process is decreasing at rate q. We think about the total customer count at time t. Now, so that's going to be our Markov chain. We're going to take a function h, and you should think of this function h perhaps as a cost function or reward function. Let's think about rewards. H is the reward rate function. And I want to introduce this function over here. This is the relative value function. What is the relative value function? Well, let's break it down. In the integrand, we have this average expected reward. So this is the distribution, the steady state distribution of the queue length, and we're looking at the long run average reward. Over here, we've got the reward at time t, given that you start the process from some state q, which can be very far away from steady state. And the relative value function, this integral, measures the value of starting at some state q relative to the long run average value. And if you're familiar with the Markov decision processes, this is coming from there, right? Okay, well, why is this a big player? We'll see in a moment. I'm going to make one assumption, this integrability assumption. So if we take absolute values inside the integral, everything should be finite. This is not a big assumption. In practice, it gets verified. Literally every time I've worked with this object, I've verified this assumption. So I haven't seen a case yet where this is broken, although I'm sure you can construct some. And I want to use it so that I can interchange the expectation and integral, right? Fubini-Tonelli allows me to do this with this assumption. So now, why is this function important? This function is important because it solves the Poisson equation or the Stein equation, depending which community you're from. And I want to show you the quickest proof that I know of that the function solves the equation, just so that we're on the same page. I'm going to break this integral from 0 to infinity into two chunks, from 0 to tau epsilon and from tau epsilon onwards. What is this tau epsilon? Well, tau epsilon, this is a truncated first jump time. Okay, if tau is the first jump time of the Markov chain, either the arrival or the death happens. And epsilon is some constant that we're going to take to 0. Right? Now, I want to focus on the second term. The first term is straightforward. Why? Because until a jump happens, your state Q of t is the same as your initial state. So there's no randomness here, except for the time. Let me focus on the second term. Right? So here's the second term written down. The first thing I want to do, I just want to change the limits of integration, going now from 0 to infinity. And I do this with a change of variables. That's all. Then the second step, I've done a few things at once. So let me walk you through them. First thing, I use the tau property. There's two expectations now. Never mind that one of them is inside the integral for the moment. But there's two expectations. And you can see that the inner expectation conditions and all the history up to the first up to tau epsilon, right? Initially, both expectations were outside, but I said, I'm going to assume that I can interchange integrals and expectations, no problem. So I took one of them inside. And now what do I have? Well, this integral, again, is going from 0 to infinity. This is nothing else other than the relative value function started at some different initial state. And using the strong Markov property, this is the only real property about this Markov chain that I'm using is the strong Markov property, meaning that the similar logic should hold for any Markov process. So a diffusion process or even a deterministic dynamical system like a fluid model. But we're going to stick to Markov chains. Okay. So the strong Markov property tells us that this is simply the relative value function initiated at the kind of next jump. If you remember the proof of Bellman's equation, right, this is pretty much the same thing, minus the control part. Anyway, well, where were we and where do we get? So by splitting up the integral to two parts, I've got the relative value function over here, and this equals something. Now, I'm going to rearrange terms into something that's more convenient, and I'm going to divide both sides by epsilon. And we get, as epsilon goes to 0, we get something that's known as the Poisson equation. So let's focus on the right-hand side first. As epsilon goes to 0, this object, this truncated hitting time converges to 1 in probability. It's not hard to show. And on the left side, what you see over here on the left side is similar to like, you want to apply Dinkin's formula almost, or Ito's lemma, say, right? But this converges to the generator. And this equality is known as the Poisson equation. Okay, so what we've shown is the relative value function is nice because it solves the Poisson equation. Now, let's start talking about generators. The generator, and I'm going to use this a lot. So the generator of a Markov chain here is another way to characterize the Markov chain. With rate lambda, we get one extra customer. With rate q, the death rate, we lose one customer. Okay. So what did we get? We got the Stein equation or the Poisson equation, and I use these terms interchangeably. For any reasonable reward function h, and I'm going to be vague about what I mean by reasonable, the relative value function solves the Poisson equation. And the key here is that this holds for all integers, non-negative integers q, right? Because that's the state space of the Markov chain. Now, equation number 1, as I mentioned before, holds more generally for diffusion processes in particular. A lot of my previous work starts with the Poisson equation for the diffusion process. Kind of goes from there. Now, why is equation number 1 useful to us? Because suppose we have a random variable, any random variable on the non-negative integers. We can simply take expectations on both sides with respect to this w, and we see that if we want to bound or say something about how close w is to q, then we can just focus on bounding the right-hand side. Okay, and how do we bound the right-hand side? Well, this is this generator comparison framework. We're going to find the generator for w. The little, I guess, nugget that I want to kind of my bit of contribution to this is that we can actually upgrade this to handle any W, any real value W. This feels like it should be true, but it's not, I guess, trivially obvious at first, because the Markov chain is defined only on the integers. It has no notion of what exists outside the integers. And so extending its definition to the entire continuum, we can do this, okay? I think that's all I care to say, that we can do this, and the details, I'll reference you some paper. So we've got the Poisson equation. We can compare our Markov chain to any random variable W. And this is a talk about diffusion approximation. So very quickly, I want to say, how do we find the diffusion approximation we want to use? Dave, question.
Yeah, I was just wondering if quickly, is there like a simple intuition around, like, you know, the fact that relative value function solves the Poisson equation? Like, in words, is there kind of maybe a non-rigorous but simple intuition of what that means physically, maybe in terms of some infinitesimal drift or something like that?
Okay, I'm going to make one attempt, but for the intuition, I will send you to a textbook on MDPs where maybe they discuss the intuition. Why is Bellman's equation true? So that's the intuition, the same. And let me say it, my understanding is the relative value function is the total, is this integral over all of your rewards over time. And if you look at the infinitesimal drift, which is like the derivative of this integral, right, then the marginal kind of increments that you see over time are exactly this integrand.
Okay, so just to be clear, what you're saying is that what you were saying about the relative value function and the Poisson equation, that is simply following from Bellman's, that's just basic dynamic programming, or is what you're saying?
I believe the intuition is one for one.
Okay.
Exactly.
Okay.
Okay. So now, again, this is maybe many of you have seen this. I'll be quick. So given the Markov chain, how do you find the diffusion approximation for it? And this is done using Taylor expansion on the generator of the Markov chain. Now, when we talk about diffusion approximations, the important thing to note is, right, when you have the central limit theorem, say a sum of IID random variables converges to a normal, you state the theorem not for the sum, but you subtract the mean and divide by the standard deviation. You normalize it. So same thing here. We subtract the fluid equilibrium and we divide by stochastic fluctuations around the fluid equilibrium. In our case, this delta is 1 over square root of lambda. Think of x as simply the normalized version. Right?
Make the coffee.
The dynamics are the same. Again, we have the important thing is that with rate lambda, you have an extra customer, and in this case, an extra customer is an extra delta. This is the death rate. You lose one customer. Now, let me suppose for the moment, this is kind of an ad hoc derivation, if you will. Suppose everything's extended to the real line, and I have this third order Taylor expansion. In fact, I would argue you can go fourth, and maybe you should sometimes, but let's stick with third. Then if we apply the Taylor expansion to the Markov chain generator and we group terms together by derivatives, so please trust me on the algebra, I've done this many times and the slides haven't changed since day one, so it's correct. The first derivative has this negative x term, right? We have something multiplied by the second derivative and then third derivatives onwards, okay? And we're going to use this expansion to derive the diffusion approximation. And for the graduate students in the audience, perhaps, let me quickly say why this gives us a diffusion process. So what is a diffusion process? A diffusion process is a solution to this stochastic integral equation or differential equation. You can write it either way. It has two components. This B is known as the drift. This is the B, the drift represents the infinitesimal change in behavior. The sigma is the volatility or the variance or the diffusion coefficient. And this W is Brownian motion. And this could be d-dimensional more generally. But for the sake of simplicity, I'm going to focus on one-dimensional diffusions. So the diffusion generator applies the drift, ties the drift to the first derivative and the diffusion coefficient of the second derivative. Now I have sigma and sigma squared. I'm going to call them both diffusion coefficient. There will be no ambiguity because of that. Now, I want to show you how Ito's formula gives us a very useful and important characterization of the stationary distribution. Right? So this is the Ito formula that everybody knows. It says that the generator satisfies certain properties. Now, suppose that a stationary distribution exists, a unique one. We initialize the state according to the stationary distribution. And let's suppose we can interchange again the integral and expectation. It results in this equation over here. Some of you may know this as, say, the basic adjoint relationship or the bar. Some of you, if you have heard of the drift method, this is the one step, or the infinitesimal drift equals 0 in steady state. Whatever the name, simply remember this fact that we're going to use going forward. And now we're on the last slide. I just want to summarize everything together. I'm going to go on a 1 to 2 minute break so that people can digest this. So let me go over the steps. All right. We started with the Markov chain, a model, our infinite Survey Q. We said, here's the relative value function. It's some kind of magical function that satisfies nice properties and allows us to compare two random variables to one another. Then we said, let me look at the Markov chain generator and apply Taylor expansion to it. I will get something that looks like first derivative, second derivative, and let's say error. And I'm going to choose, I'm free to choose any diffusion process I want. So first thing I'm going to do is I'm going to take my diffusion generator to match the first derivative term exactly. I'm going to use a generic diffusion coefficient placeholder here, because I'll mention in a second that there isn't one correct diffusion approximation to choose. So we pick sub sigma squared, hopefully, which matches this 2 plus delta x. Then we go to the Poisson equation. The Taylor expansion was a heuristic. The Poisson equation is what allows us to go from heuristic to formal mathematical statements. And we take expected values. We wish, right, at this point, we wish we could take expected values on both sides with respect to diffusion. Why? Because diffusion is real valued, whereas the Markov chain is only defined on the grid. And apply this basic adjoint relationship, or this property of Ito's lemma that we saw in the previous slide, to say that the difference between the Markov chain and diffusion is equal to the difference of the two generators. All right. And I'm doing, well, as expected on time. I wanted to spend 20 minutes here, and this is what it's going to look like. I want to leave you with this slide. I'm going to take about 5 minutes to discuss this because there are some nuances to highlight, perhaps. Okay. So the first thing is our wish. We wish we could take expectation with respect to a continuous random variable is in fact a reality. Okay. And everything you kind of expect to happen does happen. In what sense? So first of all, let me focus on this difference between the diffusion and Markov chain. The error one can show can be broken down into two parts. There's approximation error, which relates to how well is your diffusion doing capturing the Markov chain, and another bit, which is interpolation error. Now, this interpolation error is more, I think, a result of my way of approaching this. Perhaps there's some fundamental interpolation error, but I don't want to dwell on this. Let me focus first on the approximation error. Now, the approximation error corresponds directly to the difference of the two generators. Right? You see, the first order terms are captured perfectly. The second order terms, we can see how well does sigma squared do at capturing the second order term. That's present exactly at the bottom here. And while we expect the second derivative to appear of the function, well, what is our function f in the Poisson equation? It's the relative value function. And the relative value function for the Markov chain has no notion of derivatives because it's only defined on a grid. It does, however, have the analogous notion of finite differences. If you think to numerical analysis, computer science, we use finite difference approximations to approximate derivatives. So wherever you see a derivative in the generator expansion, you could actually replace that with a corresponding finite difference. And we have third order differences. And in fact, as I said before, if you go to fourth order expansion, you can even get fourth order differences, right? So why did I write the third and fourth order differences this particular way? I want to show you that, I want to just highlight the fact that in front of the third and fourth order difference terms, the magnitude of this term is of order delta squared. Now, delta is 1 over square root of lambda. So delta squared is 1 over lambda. And this goes to 0 as your system gets large. We expect, and indeed this is true, that the remaining term is of order 1, namely is bounded by a constant, doesn't grow as delta goes to 0. So this second line representing the error over here is actually of order square. And what does this tell us? This tells us that depending on how we choose the diffusion coefficient, we can actually shrink the approximation error by an order of magnitude, perhaps. And I'll quickly say why this is true. Jim has talked about this in a previous seminar. But see, if you pick the diffusion coefficient to simply equals 2, just a constant, then you're left with this order delta term as error. And that becomes the biggest error term that you have, the bottleneck. And your error shrinks at a rate of delta, slower. However, if you pick your diffusion coefficient to capture everything here, then it's as if the first term doesn't exist. And so your error is actually much smaller. And the reason I'm bringing this up again, even though we've talked about this in the past, is what I want to say in the past, if you think to Jim's talk, any diffusion, so you picking a constant diffusion coefficient is one diffusion. Picking a state-dependent diffusion coefficient gives you a different diffusion. Every time you have a new diffusion, you have to reprove these derivative bounds or gradient bounds. It's more and more work. Here, you have to bound these finite differences. We'll talk about this in a second. You have to do this one time, and then you're free to compare to any diffusion that you want with no extra effort. You're going to get, you have a tool which allows you to compare to multiple approximations with ease. All right. Let me take a 2-minute break here, as suggested by the guidelines for questions. Dave.
So just a very high level question about the kind of the Stein approach. So like conceptually, the generators, telling me the generators are close is kind of a statement about behavior in an infinitesimal sense being kind of similar, right, at a high level.
Mm-hmm.
And so I guess like, since the statement there is about more like not an infinitesimal thing, but kind of a functional, maybe just like maybe you'll talk about this when we talk about the proof. What's the high level way to do that so you don't get a weird like horizon dependence or something like this? Is it you're using some kind of stationarity relationships there, or how should we think about that at just a high level?
Well, there is no horizon dependence. You don't have something that grows as you take your time horizon getting large, because there isn't a time horizon. And so my failure to understand your question is, why would there be a dependence in the first place?
Well, so I guess maybe just at a high level, how do you translate we are similar infinitesimally over infinitesimal timescales to functionals are the same? Is there like a generic transference that is kind of known previously? Is this part of what you prove? I mean, I know that in the study of Markov chains, there are things like if our generators converge, then norm resolvent convergence or various things. Are you using? Could you just at a high level, do you comment a little on how you get from A to B? Does that question make sense? Maybe it doesn't make sense.
So my understanding of the question, there is no relationships between the results that you mentioned. No, I'm sure there is some, but
Okay.
from the technology that appears as you're applying this, there is no apparent relationship to anything else. I mean, it just is, and there is no time involved. Perhaps the generators are close infinitesimally, but you're able to take time to infinity, and infinity is a very long time in which I guess things work out. That's the best answer I can give.
Okay, thanks.
Maybe I had a quick question at this point as well. So you mentioned that norm bound sort of delta squared f of h, that doesn't change as your diffusion changes. But in principle, I guess that's because it's based on the discretization you're using. So in principle, if you had a different model discretization to begin with, or you modeled your Markov chain differently, or you had a different interpolation method, that would change potentially. Is that correct?
So what is this?
Yeah.
The finite difference does not depend on you're using discretization, and I'll talk about discretization. There's also normalization and the scaling. And ultimately the scaling, there's no funny business going on that one scaling will give you good results and another will not.
No, okay. Yeah.
As far as discretization goes, this is simply, so we can think of this here statement as there's no normalization at all. Q is just your Q length. So all of this is saying, if you take a system with 10 customers and 11 customers, how far off are they from one another? Or how far off are the relative value functions? And
I don't deny it's probably the most natural one to choose, but I just sort of wondering, like, like we have numerical analysis people here, and they say don't do finite differences, do finite element method or something like this. Is there potentially ways that could change by the interpolation method? But maybe this is a question more for the end rather than for now. I don't know.
Right. Okay. So, and just to answer this, the interpolation, what you're saying is don't do finite difference, do finite element, or do some mollified smoothing or smooth with the help of random variable. This would, I suspect this would impact what kind of error you're seeing from the interpolation bit. Okay.
Yeah.
But there's other stuff which is fundamental, independent of how you do the smoothing or the approximation, and that's what I'm calling approximation there. And these finite differences, they're independent of.
Okay, I understand. Okay, fine. Yeah, great. Okay, that's good. Thank you.
Okay. All right. So before I move on, I want to advocate maybe one message. And this is if you leave with nothing else, please leave with this message. These terms that I've highlighted in red, they're called Stein factors. In the Stein community, they're called Stein factors. If you watched perhaps some of my previous talks or Jim's talks, we use the term gradient bounds or derivative bounds when the conversation is about the Poisson equation for the diffusion. Stein factors, gradient bounds, they're one and the same. At the end of the day, you're looking at the sensitivity of the relative value function with respect to its initial condition or with respect to its arguments. Could be the first, second, third derivative. Now, in practice, the third derivative is really the one you need to get in order to get any results. Now, these Stein factors, as we'll see in a moment, are model specific. Every Markov chain has its own Stein factor. Why? Because the relative value function depends on the dynamics of the Markov chain. And I'm showing you here this theorem. The theorem is for the one-dimensional infinite server Q, but in fact, the insight holds in much broader generality. It holds for pretty much arbitrary Markov chains, that the approximation error of your diffusion depends like so on your Stein factors. Okay, there's something else that appears in the error, and notably you've got the moments of the diffusion. So this other component we refer to as moment bounds sometimes. right? The moments of the diffusion are there, you need to deal with them. But what I'm saying is, if you've managed to get the Stein factors, I think those are much harder. And if you manage to get the Stein factors, you're probably in a place where you already have the technology to get the moment bounds with relative ease. And what I want to advocate is Stein factors. I want to say that they're a fundamental property of every Markov chain. So if we think about, say, queuing networks, right? What is the first order of business? Is this network stable? So people are chasing stability. Then people chase, say, tightness of stationary distribution so that you can do limit interchange as one example. What I'm saying is there's a third property, these Stein factors. Once you unlock or are able to bound the Stein factors for a particular Markov chain, you've unlocked these convergence rates. I say this with a grain of salt, right? There's a lot of other stuff in the background, but essentially the Stein factors are the single biggest barrier to everything. And I'll show you a reference to the paper where the paper basically gives you the tools. How do you do this interpolation? It solves the problem for you so that in the future you only worry about getting Stein factors and not worrying about how you do finite difference or finite element or whatever. All right, so in the remaining example, in the remaining two examples, I want to give an example of how we bound the Stein factors for the infinite server system and now for the JSQ system. And I'm adopting this viewpoint. Basically, you give me a Markov chain, I want to attack the Stein factors. Once I have those, I've got everything. So for the infinite server system, and I want to say that this idea, or this system, in fact, was analyzed in 1988 by Andrew Barbour. And why am I talking to you in 2022 about this infinite server system? Well, although the Stein factors were known in 88, the kind of being able to compare a discrete value, a discrete random variable to a continuous one using these Stein factors was not something that I've seen done anywhere. But regardless, so let's see, how do we bound these Stein factors? We're going to start with the first order ones. I'm going to assume that my reward function h is Lipschitz. And I'm going to look at the first difference of my relative value function. It simply says that I have a Q customers, another Markov chain with Q plus 1 customers. I'm going to notice we have two expected values here. These are statements about the expectations. I can couple the two processes there on the same probability space. The coupling I could use, I'm free to choose whatever coupling I want. There's a natural one, which some people have called the synchronous coupling. Synchronous coupling means that basically the two underlying processes, so system 0 starts with 4 customers, system 1 starts with 5 customers. The two underlying processes share the same randomness going forward. They share the same arrivals, and any customers that come in have exactly the same service times, except for one customer, this extra customer in system 1, right? This is going to be like an outsider. And we're interested to bound this integral. We want to know, when will these two systems couple? When will system 0 and 1 couple? Because once they enter the same state, they're together forever. Well, in the infinite server queue, this is nearly trivial to say. You're asking basically, when is the blue diamond leaving the system? Well, if the blue diamond is in the system, the blue diamond is in service because there's infinitely many servers. So we just have to wait an exponentially distributed amount of time with mean 1. And we can bound the coupling time. And therefore, as a result, we can bound the first order Stein factor. Any questions? I'm going to pause for 10 seconds. Dave.
So it sounds like conceptually, some of what you're saying would also yield bounds for just, if not mixing time, some notion of sensitivity to initial conditions in other contexts, not about necessarily like two states that are really close on a mesh. Have you formalized that, or does your work discuss that concept?
No. What you said at first is exactly correct. This is very closely related to kind of mixing time theory. And I have not even begun to scratch the surface in gaining the knowledge for myself even. I don't know of all the possible connections there are, let alone have I started to formalize them. And perhaps some in the audience who are familiar with this concept, there's the fundamental matrix. So every Markov chain has a fundamental matrix. And the fundamental matrix is simply what happens when you take this function h to equal the identity that you're in a certain set or less than or equal to some state. So this relative value function kind of generalizes perhaps the concept of a fundamental matrix. And there are very deep connections going there. This is kind of simply the means to attack, or some kind of means for us to get a grip on these things. That's all
So maybe even a much simpler version of the question. If you're bounding the difference between h of xq plus 1 and h of xq just by a very naive union bound, like adding up the increments, do you automatically get a continuity in the initial conditions on kind of the heavy traffic scale of, like, you know, if you start, if it scales like 1 over 1 minus rho, and this one starting at 1 plus epsilon, 1 over 1 minus rho, this one starting at 1 over 1 minus rho, then on the heavy traffic scale, there's a continuity, a Lipschitzness in the initial conditions in some meaningful way. Which is, I'm not asking a fancy answer. I was just like the very naive question. Yeah.
So yes, you can, using this way, get some continuity with respect to initial condition. But for that, you have to look at something that's defined. Yes, the answer is yes. Okay, so this is the first order Stein, this first order difference. And remember I said the error consists of second, third, maybe fourth, but always third order differences. And so you can say, well, that's great. We can bound the first order difference. Is there any hope of bounding higher order differences? For the infinites over Q, again, yes, and it's very easy. And let me show you the flavor of the argument. If you think back to your numerical analysis class, what is the second order difference? Well, think back to those computational stencils. You assign a weight of +1 at Q plus 2, a weight of -2 at Q plus 1, and a weight of +1 at Q. Okay, so you have this computational stencil you're carrying around, and this translates to a bunch of different Markov chains with different initial conditions. And then I can couple these things, again, synchronously, system 0, 1, 2, 3, 4. The only difference is the initial number of customers, but here you kind of have to be clever with the coupling. There are many ways to couple things, but I'm going to say that systems 1 and 2 each have extra customers, but the customers themselves are independent. The diamond and star customers are independent from one another in terms of their service durations, right? And then system 3 has both the diamond and the star. Now we look at all the possible transitions, and basically the picture is going to look the same if any arrivals or departures happens until one of two things happen. Either the diamond customer disappears or the star customer disappears. So if the diamond customer gets served, what are we left with? We're left with this picture. We have plus, minus. So these two cancel out, and the bottom two cancel out because you got the plus minus there. Similarly, if the star customer disappears first, then again, the first two components and the second two components cancel out. So your result is the coupling time. You're basically saying there's two clocks racing against each other, two exponential clocks, and I'm going to take the quicker one of the two. And as a result, your second order difference is bounded. So in this particular example, high order differences can follow from a very similar analysis with little to no added effort. But I want to make a statement that this is not the reality of more complicated models. So as maybe I'll show you a little bit now. In practice, the first order Stein factors, although they're hard to bound, they're actually easier than second and third order Stein factors. So there's a rather big jump in difficulty. And whether you're able to address that difficulty or not, at this moment, to me, it's, did you get lucky? Or is your model nice enough that you can analyze it? Okay. So finally, 42 minutes in, let's get into the join the shortest queue system. And this I want to pitch to you as another example. I only have 4 more slides where there are no pictures, but this should all be proved by picture at this point. So to talk about the join the shortest queue model, first I want to give you a sense of the dynamics, because ultimately, right, we're chasing the Stein factors. Why? Because the approximation error depends on the Stein factors. So we have n servers. We're going to assume that everyone has a finite buffer of size b. This assumption makes life easier in terms of proving things, although I don't think it's necessary for the results. Poisson arrivals, service times are IAD, exponentially distributed with rate 1. And what is the state of the system? Well, for many of you who worked in parallel server systems, this is intuitive. But this is basically a collection of servers. The vertical columns, each vertical column represents a single server. And this horizontal line represents who's being worked on and not. So anyone below the horizontal line means that they're being actively worked on by the server. Anybody above the horizontal line, that's the buffer. Right? So this server, for example, is completely idle. And the state space of the system, you can either count to be able to generate this picture, you can either count how many customers there are in each column vertically, but it's more convenient to count horizontally. How many customers are there in each layer? So Q1 represents, for example, the number of servers that are busy. Q2 represents the number of servers that have 1 or more customers system. 1 or more customers in the queue. Let me discuss the dynamics. Okay. First, so there's two things that can happen. Either somebody completes service or an arrivals happens. How do departures look like? Well, departures are what you would expect them to be. Server number 1 just completed 2 services. So we kind of take people off from the top of the queue, what it seems like in the picture, right? This is first in, first out, so everybody feeds forward, but it's not wrong mentally to think like you're picking people off the top here. Right? Server number 2 completed service. So you see, as services happen, the corresponding customers depart. Now arrivals. This is where join the shortest queue, the policy itself, comes into play. When a new customer arrives, you send them to the server with the least number of customers. The tie-breaking rule is arbitrary, although we're going to tweak that a little bit. We're going to pick a rule to satisfy our purposes. But the point is that arrivals happen very much like you would fill water, right? In fact, the term is used by authors, right? The lower levels fill up first, and the upper levels, etc. Okay, so those are the dynamics. Now, I want to very quickly tell you what is it that we're after. So we're going to let X have the stationary distribution of this normalized queue length process. The normalization is the standard one in the literature, in that the first coordinate we're looking at basically the number of idle servers scaled by square root of n, and the rest are all simply scaled by square root of n. There's no centering. This is all happening in the Halfin-Whitt regime. Okay, and all I care about is the purpose of the slide. Don't pay attention to maybe the notation. Don't get hung up on what is being centered by what. Simply, this is the random variable I'm after. Similarly, this has a diffusion limit in the Halfin-Whitt regime. Again, don't get hung up on the stochastic integral equation. I simply want to say that there's a stationary distribution. It is b plus 1 dimensional, but it is in fact only 2-dimensional in that the third component onwards is 0. So there is state space collapse. In the Halfin-Whitt regime, the routing of customers by JSQ is efficient, and in the Halfin-Whitt regime, there's not that much traffic, meaning that almost no queue is going to see 2 or more customers waiting. Okay, but this is our Y and this is our X, and really that's all I wanted to introduce to you. And the slide here is more for archival purposes. Okay, and now the theorem says that the distance between X and Y goes to 0 at a rate of 1 over square root of n. Now the constant depends on the buffer length B, which is annoying. I don't think this is the truth. And in fact, with a debunker and science help, I think we can kill this dependence on B, but it does depend on beta in a non-trivial way. Now you can ask, well, what kind of functions H are you looking over? And I'm taking all functions H which have bounded first derivative and bounded second derivative. So this is some kind of smooth function metric. The point is that this metric, this class of functions is rich enough to imply convergence in distribution. So it's somewhat similar to the Wasserstein distance, perhaps. And again, like the previous result that I showed you, the generator expansion, first of all, gave us the diffusion. And the error, the generator expansion tells us that the error depends on the moments of your diffusion limit and the Stein factors of the Markov chain. I'm going to focus on the Stein factors. I just want to say one little thing. I'm showing convergence to a diffusion limit. And so this is, in some sense, a nice little cheat to make your life easier, but it's also pretty cool. I'm showing convergence to a diffusion limit. Right? In the Halfin-Whitt regime, there is a single limit. There are, of course, the diffusion models, which also tend towards the limit in parallel. But by showing convergence to a single limit, all of these moment bounds that come up, I no longer have to bound these moments uniformly in some kind of parameter. There's just one random variable to bound, so it's enough to show that it has finite moments. If you worked in this, you will appreciate that how much of a headache this saves you. Okay, so let me prove by picture the Stein factors, and I'm roughly on schedule. So again, I want to use this notion of a synchronous coupling, exactly like in the infinite server setting. Right? I have two systems, Q and Q prime. I'm going to call them the red and blue systems. Right? So the red system is the system with all of these red customers. The blue system is the same plus that extra one blue customer. Right? Now, all arrivals are coupled so that whenever one system sees an arrival, the second one does as well, and the service times are coupled as well. So to understand, and what we're interested when bounding this integral, we're interested again in the statement, when are these two chains going to couple in expectation, or what is the expected coupling time of these two chains? All right, well, one way to kind of understand that is to simulate the dynamics. So let's do a sample path of what can happen. And I want to show you that this coupling satisfies a certain non-expansive property. So this coupling is non-expansive in that if the red and blue systems start with one customer apart, as they evolve, they will never drift more than one customer apart. In fact, this particular system satisfies this monotonicity property, where the red system is lower in some sense than the blue system, and that's going to be the case until the very end. So I want to show you that until they couple, the gap is always on customer. Let's look at what happens when departures happen. So server number one finished service. That was the case in both systems, right? Both systems lose a customer from buffer one. Server number two finishes service, somebody else finishes service, etc. So you see, service completions don't break this the gap. They don't make the gap between the two systems increase. Okay, David, yeah.
Just real quick, what if that one person has a massive service time, or like why would that not necessarily cause any problems in some sense?
Because in this case we're doing FIFO, and in fact I was chatting with Varun a few weeks ago, and he was talking about processor sharing. So in processor sharing, you don't have this non-expansive property, and I told to him, Varun, I have no idea how to handle this. So this is a great one. Okay, so now let's look at what happens when arrivals happen. Well, a customer arrives. Remember, this is water filling. Another customer arrives. But here I'm selecting this arbitrary tie-breaking rule to go in my favor. Okay, what I'm saying is, think about the red system. And in the red system, there is no blue customer. In the red system, we have 3 servers who have no customers, least loaded. And so any arrival could potentially be routed to any one of the 3. But I'm going to choose the tie-breaking rule in a way that I save the server with the blue customer till the very end. Okay, but that's okay. You can do that. Now, again, let me come back here. In the red system, when the new customer comes in, it's obvious. There's only one server now with no customers. So the red system will get somebody here. In the blue system, the new customer is going to be allocated to one of many possible servers. Again, we're going to say, well, no, it's going to be allocated exactly to this blue customer, to the server with the blue customer. Furthermore, I'm going to treat this blue customer as if this is like a low priority customer with preemptive resume service. So in other words, if the blue customer is in service and somebody else comes in, the blue customer is bounced out of service. And this is why in FIFO, to Dave's previous question, even if this blue customer has a massive service, like a massive workload, it won't matter because the blue customer only gets served when it's not bothering anybody in the system.
So to be clear, it's a preemptive, this is a preemptive system you're looking at.
Preemptive, yeah, preemptive.
I understand. Okay.
Yeah.
Just to ask for the distributions to match up and everything, and to continue with the FIFO property, I guess you're assuming that everything's exponential.
Exponential is key, you're right. Yeah, exactly. Moving to general distributions, you can probably do something, but it requires something very clever as well. Right. So I think I gave you all the idea. So this thing is non-expensive. You only have to wait until this one blue customer leaves the system. When does the customer leave the system? Well, whenever that customer can only leave the system from a state where it is being served. Right. So the customer can only leave a system when it's being served, and in the red system, there's going to be idleness there. However, not all such states, so this is an example of a state where the blue customer is being served and could potentially leave the system. However, not all such states are equally good. This is, by the way, another example where the blue customer is being served. And this is another example where the blue customer is being served. But I'm going to talk about why the first 2 are bad. Okay. Here, and this is what makes, at this point, the analysis non-trivial. Somewhat complicated. Well, it's simple once you do it, right? Everything is simple once you solve it. So the reason that this is a bad state is because although the blue customer is being served, how the service time is exponentially distributed with mean 1. So you need an order 1 time to remain in service. But the second somebody comes in, arrives to the system, the blue customer is being kicked out, right? And in the Halfin-Whitt regime, the arrival rate is order n, and the service rate at best is also order n, right here. So if you think about the first row, focus only on the first row, think of this as a birth-death process. With rate n lambda is going to be increasing, with rate n at best, it's going to be decreasing. But because you started when all servers are busy for the blue system, the time until the blue customer gets kicked out of service, you can show is only 1 over square root of n. So though it's in service, it doesn't have nearly enough time in the state to actually have a chance of coupling or completing service. So this case is also bad. I'll just mention why. Although there's plenty of kind of room, plenty of space to go before the blue customer gets kicked out, you see that there are too many servers which have customers waiting in the buffer. So again, if you focus only on the first row and think of this as the birth-death process, It is increasing at rate n, but it isn't decreasing necessarily when the service completions here happen, because when one of these busy servers completes service, there's a new customer that enters the buffer right away. So they don't serve to decrement the horizontal row, right? Perhaps I should refer you to, say, reading the paper for more details, but simply to say that this is also an example of a bad state where you need order one time to couple. How long you get, didn't really bother trying to chase that. What we want are these good states. So in the Halfin-Whitt regime, we have n servers. So we want a state with order square root of n idle servers and order square root of n servers with one customer in their buffer. This is a good state for us, because if you're in one of, this isn't a single state, this is like a class of states. If you're in one of these states, the chance that you're able to couple before the blue customer gets kicked out of service is non-trivial. In fact, you can bound it from below by some constant probability that doesn't depend on the number of servers in. Okay, and then this is the whole key. And we put this together, we get this nice little regenerative-like argument, which says, so first of all, the Stein factor is bounded by something. And the proof outline is as follows. You construct a synchronous coupling. Starting from any state, you wait for the first time to hit this good state, which I just shown to you on the previous slide. And this hitting time is at most something, right? Some object. How do you show this? Well, it's equivalent to saying there's some compact state in my state space, and given any initial condition, what is the expected hitting time to a compact state space? In this particular instance, I used the Lyapunov function. Now, from a good state, once you're in a good state, this is where the regeneration structure comes in, kind of. If you're in a good state, you can either couple before all servers get busy and you're kicked out of a good state, or you fail to couple, but then you simply wait till you're in a good state again. And because the probability of coupling is bounded by a constant, and because the duration of these trials can also be bounded independent of n, at the end of the day, you can get the expected coupling time is bounded. Okay. I want to close off by saying a few words on the high order Stein factors. I said that they're not easy in general. And in this system, I think I did get somewhat lucky. That's good. So how do you access higher order Stein factors? Although I never showed it to you before, the Poisson equation for this particular system looks as follows. So this left-hand side is what we've seen before. The right-hand side, ignore these coefficients. They are not really, well, they are important, but they're not the point. Focus on the differences, right? You see that you've got first order difference and first order difference at the bottom, and then the first term is a second order difference. You could think of this very much as being the second order differential equation for the diffusion, because in fact it bears a lot of resemblance. And this particular structure allows us to write the first order difference, the second order difference in the first direction as a function of lower order differences. So we can bootstrap, but we can only bootstrap for the second order difference in the first coordinate. How do we get the others? Well, we can relate all of them to one another using synchronous couplings. And just a quick insight into how that's done. Right? Even though you initialize your systems, your coupled systems, maybe with extra customers along the first dimension, over time as they evolve, they can change to be like coupled systems with extra customers along the second dimension, and the first dimension being perfectly coupled. So you're essentially kind of deriving like extra systems of equations to find some dependence between these high order Stein factors. And the takeaway, okay, we need to rely on the join the shortest queue dynamics for higher order bounds in this problem. Notice not necessarily Halfin-Whitt, right? Simply JSQ, which let me end by saying one open problem, especially real to many people who work in parallel server systems, is the fact that at the moment we have no universal result. In what sense universal? So people have been using the word universal to mean that, well, I can handle a range of regimes which is between Halfin-Whitt and non-degenerate slowdown, or beyond non-degenerate slowdown. Ideally, and for this, a lot of the times people will impose this kind of assume that the arrival rate scales like this, and there's this alpha and beta. But these are ultimately somewhat artificial, right? In reality, there's only lambda, the arrival rate, and there's only n, the number of servers. And we can normalize the service rate to be 1. There's only 2 numbers. And in fact, maybe the utilization and the number of servers are the more appropriate ones. Can you find, or can you prove something which holds true for all n and rho, and show how the interaction there happens? And I think the answer to that, given the complexity that we've observed in kind of with everybody working on this, I think the answer to that is maybe this is going to be really tough to show, but there is hope at least that something could be done using the tools that I presented. So that's all I want to say. Thank you very much.
Okay, so thanks very much, Anton. Okay. Okay, so I had a few questions as we went along, but are there any other questions?
Yeah, I promised Neil it will be a 45-minute talk.
That's why we say 45 minutes, you see. That's good. I mean, I had one, I guess, one quick question. There's 2 separate things. Am I right in thinking that, I mean, okay, there's one thing that you're sort of getting these kind of Stein terms, and that you're dealing with those through this kind of finite difference approximation, essentially. And there's the second bit, which is the coupling part. You don't have to go down the coupling route, I guess. It's just you've chosen to do that for this model, and then that happens to work out for joint shortest queue infinite server queues, but might not be the way to go for other things. Is that correct? So they're kind of 2 different things there.
Yeah, correct.
Yeah. Okay. Yeah. Okay. So it's kind of a choice as to how you deal with those. Yeah. And then maybe another quick question. Are there other types of systems?
Yeah, I would rather other people ask, but maybe
sorry. Yeah. You go, Dave. Yeah. Did you have a question, Dave?
Oh yeah, but I mean, other people can.
Okay. Yeah.
Okay, if absolutely nobody has a question, then yeah. So, okay, so I guess the way that you presented it, if you have these Stein factors, you recover kind of some weak convergence results and you get the error bounds, which makes sense. Either formally or even heuristically, although I guess heuristically it's presumably intuitive. What about the converse? Namely, there's a lot of results in the literature for which there's some kind of weak convergence and maybe some kind of non-explicit error bounds proven by some characteristic function, complex analysis stuff, or whatever it is. What are your thoughts on, well, uniform bounds must imply the Stein factors are well behaved?
I think you can do that. You can, it's been on my mind that somehow, if there's a model for which a lot of work has been done by others, can you not reverse engineer those results? Because ultimately, although my everything I showed has inequalities, ultimately you're dealing with equalities. So you can, in theory, reverse engineer it. some previous results. In practice, I haven't done it simply because there wasn't a good opportunity, perhaps.
That's an interesting question, but I'm not sure it is necessarily possible. Quite one of the big questions people have in this is can you prove things in like Kolmogorov distance, which is what Anton's working like a Wasserstein type distance where you've got smooth test functions H, whereas if in Kolmogorov distance you've got non-smooth test functions, and people have proved various theorems, etc., using characteristic function techniques. And you might hope, okay, well, maybe we could reverse engineer and get some Stein factor bounding for Kolmogorov type test functions. That's not possible. So people, when they've proven a Kolmogorov type distance bound by Stein's method, they have to go and find ways of you have to come up with alternative forms of expansions to avoid those derivative terms they can't handle. So I'm not sure it would be possible. That's an excellent question.
That's a really interesting point.
To follow up on Robert's point, the key here is really what function H you choose. So going from Wasserstein to Kolmogorov, Wasserstein you choose H to be Lipschitz. Kolmogorov you choose H to be an indicator. This is why there's this huge difficulty. You cannot take something that you showed for a Lipschitz function and simply translate it to the Kolmogorov, to the indicator setting.
That was actually my next question, which I assume most people knew the answer to, and I just, I'm not that familiar with some of these things. Does this result apply to the obvious tail, where you would need H to be an indicator, or can you do an approximation argument, or no, that breaks down here? Maybe you started the talk and I missed it.
I think the seeds are here for someone to potentially, I think that you can have some results. I'm not saying whether they're going to be the best possible, but I think this has the potential to be taken and used to other types of functions, maybe tail probabilities or indicator functions. I haven't done this. It's a boatload of work, and like Robert said, there is a huge leap in difficulty when you go from a Lipschitz test function to an indicator test function. I will comment that here we're using a discrete structure. So every function is discontinuous if it's only defined on a grid. You could say that, but that's not quite true. Well, there is this discontinuity that's going to bite you somehow, even though you're using this grid valued stuff here.
So there's an interesting sort of footnote, which is that Stein introduced his great methods. It's the golden anniversary. It's 50 years since Stein's method was introduced, and it was so in only 2 years after he introduced his method, a proof of the central limit theorem by Stein's method with an optimal order bound in the Wasserstein distance was proved. That's just 2 years after he introduced his method. It took another 10 years for them to get an optimal order Kolmogorov distance bound via Stein's technique. And Anton's work, I've had a bit of a look at his papers. This is a lot harder than proving the central limit theorem. It maybe it's possible. It's a lot. It's a lot of work. I think it's very non-trivial to get this to work. But Kolmogorov type distance bounds are often limited to sort of tractable applications in, for example, normal approximation or something like that. This seems the type of it's a sufficiently challenging problem that it would be a great achievement to get results in stronger metrics than Anton's been able to achieve. There are, by the way, the easy techniques to straight away get a Kolmogorov distance bound from what Anton's got, but you'll just get you won't get the optimal order. So you'll get maybe a square, is your balance rather than having a 1 over lambda square rooted, you'll get a lambda to the quarter or something. So you don't quite get the correct rate.
This is the easy result for the taking. That's currently.
Yeah, it's an easy way of doing it, but anything better is challenging.
Since I'm getting such interesting dialogue, I'll simply continue then, unless Robert,
Yeah.
I would
Should we just say we're skipping to for everyone's, for the sake of everyone, we'll thank Anton one more time and skip to the
Yeah, of course. I
discussion
assume that was implicit. Yeah.
We're kind of pretty much headed into the discussion part already. So in case, people, hang on.
But I guess, I would encourage Robert, very piercing insights. Do you have a question? Before I put out another one, I'll simply ask you to throw something out there because I'm learning a lot. Yeah.
I don't know. I mean, I don't know if I have a question, but just coming back to your comment earlier about higher level of this generator approach. This is like an interesting point. It's actually, when you're doing Stein's method, there's like key insight is what Anton effectively starting off with doing. He wants to bound the distance between the expectation of H of his prelimit, an expectation of his diffusion limit. Okay, and he does this by introducing a generator, and this is like this generator is, you can call it Poisson equation, you can call it Stein equation, and this is always how you start off Stein's method. And this generator is in some sense characterizing your limit distribution. What's happened there is you've got one key jump, is that it's quite challenging directly to bound the expectation of H of X minus expectation H of Y, because you've got two different random variables, and that's awkward to deal with. So what the very first step that Anton's doing is by introducing this generator, he's reduced it to a single, you have to bound a single expectation involving a single random variable, okay? Which just so happens to be a often simpler thing to do. Where you keep the other random, you don't lose the other random variable, though that appears in your Stein factors. Okay, so you basically transfer the whole approximation problem into two separate problems. You've got a Stein factor problem, it's a sense involving one part of one of your distributions, and like a boundary generator problem involving your other random variable.
Yeah.
Yep.
I was say maybe following up just as you're saying, because it's something that's very much on my mind a little bit. I mean, as I think about anything in this space a little, right, you could, in some sense, enforcing that in steady state, the expected change in H is 0 is like a set of, it's like a set of linear equations, right? Like this is this bar thing. I know you talk about Anton, but is one way to think about why generator closeness yields functional closeness is that like they're two similar linear systems, and you're just bounding how much perturbing the linear system, which comes from the set of equalities, expected steady state drift change in H is 0. Is it like really this is a perturbation in a linear optimization kind of thing? Is that the way to think about that first step?
I think the extra thing you missed is you're bounding the perturbation of these things applied to special functions. It can't be any function. It has to be special, like special functions. That's
okay. So maybe then this question is a pretty naive one. Maybe it was already implicit in what you said. Do you really need uniform control over this coupling, or can you have rare states have crummier behavior and you just need the expected time to get to a good state under the stationary measure I can control?
The latter. The latter.
Did you say that explicitly and I missed it, or was it you didn't really? Okay.
I didn't say that explicitly.
Okay.
There's only so many things I can say.
Of course. But then I guess, was it necessary to control the bad states, or is because you seem to talk about controlling the bad states in some sense.
No, I don't care about the bad states. I simply said that not all states where coupling can happen are equal. So what happens is it could couple in a bad state. I'm just not measuring that. I said, here's a chunk of class. I said, here's a compact set of states to which I can guarantee that you're going to return, and I can bound the expected return time. And on this chunk of compact states, good things happen. And I'm throwing out so much more that could happen potentially. So this is why it's crude. So,
okay. So then final 2 points, then really I'll be done, are kind of like very high level things, but that I think at least there are things I've always wondered about or at least the first thing is, so is there a paper out there, maybe it would be a clunky paper that either observes, or maybe it's kind of a folk theorem, that the Stein methodology that you're dealing with here, is there some way to make precise that is a coupling of a certain continuous system to a certain discrete system, just in the sense, like I know in some sense when you talk about you could use any diffusion model approximation, it's somehow implicit, but like, is there a paper that makes that concept of you're really just coupling a certain way to bucket the continuous system to the discrete system, in the same way that, like, when I think about the KMT coupling, Komlos, the whatever, too snotty thing, and I know like it really requires these extremely elaborate ways to discretize a normal. Is there any work out there that shows, in some cosmic sense, what people are doing in Stein world is a more elaborate version of that, and one could have done KMT coupling? So is there a Stein proof of KMT coupling? Does that?
I have no idea. I understand your question, and my answer is I don't know.
Okay. And then the final, very final point, speaking to your thing about different heavy traffic regimes, which is, something I always find interesting. So like, have you done this, and this would be totally heuristic, and I agree the real thing would probably be quite challenging. Do the Stein factors, do the bounds you get for the Stein factors, do you have any sense for whether they agree at the boundary? Like, as you're kind of, did you try to pencil out that heuristic exploration of like, well, the way we, and yeah.
I quite like to jump in on that, because I was going to ask something that's basically the program you're going for, isn't it? You're basically saying that these Stein factors, if in every, and all this Stein stuff is limit independent, doesn't care about what the limit is really. And so you're basically saying, if I can, in all of these regimes, if I can find out the appropriate way to squash down these Stein factors, then I'm going to get out the appropriate limit in each result, in each regime. Is that basically the kind of holy grail kind of thing you're going for?
So I think that is a correct state, or I think at least a correct spirit of thinking about it.
Yeah, okay.
But I will comment that it is extremely difficult.
Yeah, I'm not saying it's easy. I'm just saying, like, that's probably like the, maybe aside from the kind of novelty of using continuous rather than discrete and things like this, there's this other aspect that you're going for as well.
That's ultimately, but that's like,
yeah, that's fine though. It's okay.
And ultimately, to follow up on this, it's simply driven by this question: when you have 60 servers and your arrival rate is 50.
Yeah, you're not in any regime. Yeah.
Which of these darn regimes are you in? Because all of them tell you to use different approximations. And so, first of all, the easy answer is just, do the generator expansion and use whatever diffusion you get from there. The question is, how do you prove it? Well, at least we know how to approximate it.
Yeah, okay. That makes sense.
And to prove it, you may be able to anchor things. So if you can say a result about NDS, Halfin-Whitt, maybe mean field, and maybe you can get results here. And whatever diffusion limit this gives you maybe falls between two anchor points. That's kind of a crude way of thinking about this.
Okay, great, good. I have to run, I'm afraid. I can, if you want to stay in chat, I can make one of you hosts or something like this.
You can leave me the host if
people want to just chat and catch up or anything. Yeah, maybe I'll do that. Okay, just a sec.
Robert, actually, since you're here, I wanted to ask what your take is on the higher order Stein factor stuff, because I know, and I've asked you about your paper in the past, where you can say, well, you can just treat them as first order ones.
All right, okay.
But in practice, for me, that it seems like it doesn't work well for for all possible cases, or at least many that.
No, I can imagine that there are. Yeah, I do remember you sending me that email asking about it. Yeah, somehow I don't. Yeah, somehow I don't think would be possible. It would make your life an awful lot easier if it was.
Of course, yeah.
Yeah, I mean, in my paper, it was for sort of when you were looking at continuous distributions and you had nice linear Stein equations. Yeah,
Okay, fair enough. I just wanted to ask if you gave this more thought and maybe something along those
I mean,
lines.
I didn't actually. Because I kind of, I mean, I didn't, but I might do. But it'd be more for me to understand why my work doesn't work. Because I just somehow when I see this, I just can't believe it could work. Because I see that what you're doing is significantly more complicated than the sort of Stein factor bounds that the Stein equations that we were looking at. So they must, and I know that you've got a pretty heavy analysis going on here. So I kind of had assumed that you'd had a bit of a look at it, because you wouldn't want to delve into this analysis if there was something like just that you could knock out very quickly. So
Yeah.
but yeah, I think I've looked at your papers, and I think that they really, I mean, it's a really clear talk as well, by the way. So thank you, because they're very, very technical papers, and it sort of helps bring out what sort of the bigger picture of everything is. And I mean, I think this prelimit generator approach, it's a really good idea. Really,
Thank you.
Really interested.
Maybe you will use it. Proliferation. That's the.
Yeah.
So maybe like thinking on what you guys were just saying, is there like a natural system you could cook up that kind of, it was created for higher order Stein to work? Like a multi-scale, like I could imagine a sequence of discrete systems where on different exponential meshes, it was baked in to behave in the way you would want it to, so the different sequence kind of things in the sequence made sense, just to kind of understand precisely what is going on. Does that make sense?
I might have to go in a minute, so I think my wife's calling.
Bye, Robert. No, it doesn't. I don't quite understand.
Or okay, I guess like, could this method work between two discrete systems? Let me start there.
Yes.
Suppose you have a discrete system, which is like a mesh of 2 to the minus n, and a discrete system, which is a mesh of 4 to the minus n.
Yes. And you don't even need any kind of weird interpolation. Yes.
So then, yeah, I guess my point was simply like, I wonder if, to kind of get a clear, like, what does the higher order Stein thing mean if you go all the way down? Would that be a playground where you could just, because they fit into each other so naturally, there's no continuity kind of confusing things, it would just become very clear what exactly was going on. That's all I meant.
Even the whole point, I think, the whole point of what I wanted to say over here with this block, is that even when you have this continuity versus discrete system, it doesn't make your life any harder. There's so to your point of a mesh versus a finer mesh, you're not really winning anything by avoiding continuous systems, and you're not gaining any insight that I could think of, which you wouldn't otherwise have gained.
Well, but the one system is literally a discretization. I mean, what do I mean to say here? Or would the better thing be one system is a subsampling in time? I'm just wondering, is there a way to set it up so you win so easily? Like, if one system is literally the other system sampled twice as frequently in time or something. Is that the right way to think about it, where it would simplify?
By you're saying win so easily, by which you mean that
I mean, like, you could really put through even the higher order Stein factors and it would just be, it would all magically, it's not that the result would be interesting, but it would magically illustrate the subtleties, the complexities, because it would have been rigged for those things to all sync up to be understandable in some sense.
when you use the word rigged, I think you can, yes, you can rig anything, but
now there's a conjecture. I like that. Now to the life philosophy part of the talk, right? So
just going on to, in some senses, there are some things that are a bit rigged. So that what Anton was kind of asking is that I've got this paper where if you kind of are given a bound on a first order Stein factor, the paper basically automatically gives you all higher order Stein factors immediately, straight away, no work.
Huh. Okay.
But the catch is the Stein equations have to take sort of special forms for that to work out, and it's more complicated than what Anton is more complicated, so we can't do that. Yeah, it's quite nice when it works out. When I did my PhD, I spent like an entire appendix of my PhD just working out higher order Stein factor for something involving modified Bessel functions. Then I met someone in the department in Oxford where I was at the time, and he put forward this idea of modifying the Poisson equation to sort of, get this to work. And what took me like an entire appendix just comes out in nothing. It's you see, but it has to be sort of special how you set that up. What you basically do is you've kind of got your Poisson equation, is your Stein equation, and what you kind of do is you kind of differentiate both sides of it. Oh, you basically, and it's awkward to explain, but you can sort of rig your Poisson equation. You change your parameters, but keep everything the same in some sense, and you change your test functions, which are your H's, and it kind of just, I don't know, it's awkward to explain, but you can just, if you go through the process, you can kind of just get it to work straight away to peel off the higher order ones. It's quite nice, but I don't think you can do it here. So.
Anyway, guys, very stimulating talk. I'm sure I'll catch you sometime soon, Anton. And Robert, I don't know if we've ever met.
No, I've never met you, David. It's nice to meet you.
Nice to meet you. Maybe at a conference sometime in the future.
Yeah, I'll look out for you next time. So very good to see you.
Where are you?
I'm at Manchester. I'm with Neil.
Okay.
It was actually Neil. Neil told me about the talk, so I was interested to go and see. That's how I know about this.
Okay. Cool. Okay. Have a good.
Good to see you,
Robert.
And very good to see you again, Anton. All the best.
See you. Bye.